I just want to start off by saying a big thanks to Corey Timstra, Dave Schroeder, Lynn Ducharme, and all the AAF team that has supported this project, especially by being our experiment participants. So our project couldn't have gotten off the ground without the help also of our colleagues Vic Adamovich and Callie Erline, who helped us get in touch with AAF and also helped a lot with group discussions and bouncing ideas off each other. The project that I'm presenting is Experiments, Machine Learning, and Regression Analysis on Wildfire Suppression Expenditures in Alberta. We motivated this project last year when we applied for the grant by considering that climate variance and budgetary uncertainty are some of the challenges faced by Alberta wildfire. So towards addressing the question of how wildland fire operations can be made more efficient and more effective, we want to investigate empirically the drivers of what's causing wildfire suppression expenditure in Alberta. The research questions that motivated us was the consideration of how a proportion of variance in expenditures can be attributed to discretionary policy factors like operational policy versus those that are non-discretionary, like weather and other environment factors. And also, we want to explain how the discretionary expenditure can be explained by managerial effects. And delving further into that, we employed some techniques to answer the question of how behavioral impact aspects will influence incident commanders' decisions and how that overall impacts the suppression costs. So towards addressing these questions, we can generally split our approach into two parts. The first being the application of experimental methods to learn about risk behavior. And secondly, to use the data from part one and incorporate it into an expenditure analysis that will explain better how costs are being generated during fire suppression. So for part one, we're using experiments to measure risk aversion. These are standard risk elicitation methods that have been proven in experimental economics and psychology literature, including choices between lotteries and choices between lottery, play, and sure payment, and also a self-assessed domain-specific risk preference. So just a bit of background for people who may have not had the chance to play in economic experiment before. These are experiments in which we try to elicit participants' economic behavior using real money. We're giving people the option to play the game and having the chance to earn money based on their decisions. So towards doing this experiment, we reached out to Dave, who sent an email to asking all current and past incident commanders from levels 5 to level 1 to participate in this. And we had a pretty good response of 61 participants among the incident commanders. Also, we were interested in comparing and contrasting how incident commanders would behave to typical experiment participants. So we recruited from our pool of mostly made up of U of A students. Here is an example of one of the experiments, just one of 5 sets of experimental tasks actually, that we used to reveal participants' risk preferences. So for this type of task, which is called the single choice list, we're asking participants to choose which one of these 5 lotteries they would prefer to play. Now, someone who is generally probably more risk averse might elect to choose something closer to here. The first lottery, $16 or $16, whereas somebody who is less risk averse might opt for a chance to win a higher payoff, even though there's an equal 50% chance of winning a lower payoff. So this is just some general statistics that we got from our groups of control participants and incident commander participants. On general, it seems that the control sample earned a little bit more, but the median for both control and incident commanders was close to $30 that they earned from the task. We see that the control sample has more females, whereas the incident commanders who chose to participate were mostly male, different ages, and different family and education backgrounds. I'm putting this here for you to see, but these are things that we can control for later to make sure that we're comparing the right attributes. So initially, when we just plot the choices made by incident commanders, we notice that incident commanders, the orange lines, look quite different from the control samples, the green lines. So in these charts, all you have to pay attention to is, in addition to the distribution of the lines, just a difference of distribution between the orange and the green. Towards the right, these are the choices that would reveal more risk aversion, such as choosing the $16 or $16 option in the previous task. And we see that it looks like ICs and control samples are quite different. However, we know from the existing literature that gender makes up a big portion of risk aversion. So after having split up our cohorts, males to the left, females to the right, we see that actually comparing male ICs with male control, there isn't much of a significant difference in how they play the games. As well, females don't seem to have a difference with female control subjects either. In addition to looking at choice data like this, we can also apply a structural model. And I know it's close to lunch, this is the last presentation, you don't want to see too much math, but I just want to show you this is the basis of the model that we're using. It's a standard economic model that's being used from which we can apply frameworks like expected utility theory and prospect theory to analyze the choices that people make, such as through this task, into a specific number. The specific number phi is a predicted risk parameter that we can use to compare participants between tasks, how an individual participant behaves between tasks, and also compare the risk from one participant to the other, and compare how incident commanders are different from our control sample. Applying the structural estimate, we find that incident commanders don't appear to be any more or less risk averse than the general population. Females seem to be significantly more risk averse in 2 of the 4 tasks, and that's to be expected based on what we've seen in the literature. Age affects risk aversion differently in 2 of the tasks, and the literature also agrees that the effective age is ambiguous. Using the structural estimate, we can plot where the participants revealed through their choices will fall on a scale from risk-seeking behavior to risk-averse behavior. Now, in some tasks, like the INV investment game, the task is designed such that participants have more options from which a more precise range of risk parameters can be estimated. But some, like the single choice game, only have 5 categories, like the 5 lotteries we saw, and the participants are grouped more generally. Here, we're interested in seeing how participants are distributed across the 4 tasks, and we see that generally, other than the broad grouped SCL game, everybody kind of has a risk aversion revealed to be between 0 and +1. General risk neutrality, nothing too extreme in either directions, which is to be expected from what we see in the literature. So moving to part 2, this is our empirical model of expenditures based on existing literature that has also used regression models as a way to explain wildfire suppression expenditures. In our model, the left-hand side is the expenditure for each fire, and the right-hand side is our categories of variable factors, for 8 of them, in fact, that are made up of different factors from environment to jurisdiction to communities, values at risk, and also controlled by for forest management area and seasonality. To code some of this data, we had to look at some geospatial data. For instance, for values at risk, such as communities and roads, we'll code it as 1 or 0, depending on whether we see the presence of a community or a road within a certain radius. Having taken all that, we run our regression model. And I know there's a bit to unpack, so I just want to highlight a few things. First of all, we're looking at all Alberta fires starting on fire year 2015 to the end of 2020, filtering out those extreme fires above the 99th percentile for each class, as well as fires that might have complicated fire suppression expenditures, such as those that are part of complexes and those that were turned over. This table shows how certain contributors will influence the percentage of suppression expenditure variation. Here, 0.01 being 1% and 1.0 being 100%. So regression analysis, what's interesting about it is that it can inform us about the elasticity of suppression expenditure to many factors. Those that are discretionary and those that are non-discretionary. So things that Alberta Wildfire can do about and things that perhaps Alberta Wildfire cannot, such as temperature. We see that temperature is quite a significant driver of expenditure variation throughout almost all classes. Throughout all classes, and significant in 4. For instance, for small fires in Class A 1% temperature increase during the initial part of the fire, around the days around assessment date, will increase the suppression expenditure by 2.9%. But when we go up to Class E larger fires, a 1% increase can actually influence expenditures by 27%. Rain will decrease the expenditure on average. Wind speed increases it as it drives the fire environment. Relative humidity isn't significant for most classes. It is for Class C. And we see that when the fuel is timber or slash fuel instead of grass or other type of fuel, fires, it's driving a type of fire environment that's making it much more difficult and much more expensive to put out. One of the interesting variables we have is what we call resource competition. So the number of fires that are also burning at the same time as one fire. And originally, my hypothesis was that the more fires are burning, the more expensive suppression will be, because all these resources are in competition to fight the fire. But in fact, we see significantly for larger fires, for every additional fire that's burning in the province at the same time, the cost seems to be decreasing by 1.9%. So that signals to us that there's some type of economies of scale going on when there are large fires and resources are being effectively deployed in such a way that each additional fire is actually less expensive. Moving on to operation, we see that the delay between when a fire starts and when a fire is reported to Alberta Wildfire makes the fire generally more expensive. However, the decision of the incident commanders who arrive on site to delay immediate suppression action on a fire is actually a very important strategic one that is not causing suppression costs to go up. In fact, suppression costs can actually be saved when incident commanders decide that immediate action is not required for certain fires and instead to allocate those resources somewhere else. In addition, I want to highlight the community as a values at risk. When it comes to small fires that are near communities appear to be less expensive to put out. But when the fire gets large enough to the extent that it threatens a community nearby, then the fire becomes more than double expensive. And with road access, the better road access there is close to a fire, the less expensive it is, as we can imagine that it helps Alberta Wildfire respondents get there as soon as possible. Taking the estimates derived from that regression model, we see that factors on average will contribute differently for each type on each fire from Class A to Class E. So previously, in the previous model, forest management area and seasonality were all factors that were absorbed into the model as fixed effects. But here we can see how they affect estimates of fire. Forest management area, including all the characteristics that are fixed over the sample over time. So this is anything that we didn't capture in the environment or operations or competition. This could be specific geographies of a region, or perhaps a specific type of management style found in FMA that is accounting for the variation in cost. We see that across all fires, environment factors plays the biggest role in affecting what costs will be. And in fact, resource competition, so the effective distribution of resources when multiple fires are going on, is actually diminuting the suppression expenditures that would be expected otherwise. So the next steps for our project is to reconcile the economic and psychology measures of risk aversion. So far, I've shown you how we use structural models and non-structural models as a way to estimate risk based on people's choices. We also want to look at some of the demographic surveys that we put out, or rather the self-assessed risk elicitation surveys, and see how that matches with what participants revealed in the games that they played, and how that compares to the established psychology literature. Further, we want to expand the expenditure model that you've seen, including the incident commander's risk behavior as we elicited through the experiment, also including the resource and manpower deployment resource decisions that were made by Alberta Wildfire. And further, we would like to apply machine learning methods such as random forest modeling for expenditure prediction to see if there's any relationships inherent within the data that we haven't picked out on our own yet. Ultimately, we want to connect the part 1 and part 2 of our project in order to create an expenditure analysis that has a holistic view of all the contributors that are going on to affecting wildfire suppression expenditures. So thank you for this grant, and we hope to come back to you sometime with more results and a final report.